Okay, another 30 seconds or so on that. I just noticed that there's about 6, 7 of you that haven't signed in on the chat console. So if you have finished calculation, if you can just click the chat button in the top right and just sign in, just say hi, that'd be great. Okay. Shall we move forward with that then? So hopefully you got calculations that looked a little bit like this. So if you've made an error, it's possibly a power of 10 error. Often when you're squaring things, you might forget to square all of it, might just square the powers of 10 instead. Sometimes people find it easier to do the powers of 10 on a piece of paper, not putting them into the calculator, and just do the numbers bit on the calculator and do the powers of 10 in their head. What you should discover is that the repulsion between a pair of protons is around about 40 newtons. Now, 40 newtons isn't very much. That's kind of you picking up your school bag or something like that. But when you apply 40 newtons to your school bag has a mass of about 4 kilograms. And so it doesn't accelerate very much. Whereas when you apply 4 kilograms, 40 newtons to a proton, which has a very, very small mass, down at 10 to the minus 27 of a kilograms, 40 newtons to a proton is an incredible force. And, you know, for a proton, that's a massive, massive, massive influence that's going to push that proton very hard indeed. So hopefully there is an equally large force that's holding on to the protons. So we have a little look across at the gravitational attraction calculation, and we find out, to our horror, that there is a 10 to the minus 35 in the answer to that. So just putting the two calculations together, you can see that the repulsive force is 10 to the 36 times larger than the attractive force. Now, I wouldn't want you to think that 36 is a small number. Remember, that's 36 zeros. So the weird thing is that we live in a universe in which there exist two forces, and one of the forces is a 1 followed by 36 zeros times stronger than the other one. This is just a crazy nonsense universe where this could be allowed to take place. Now, when we do come on to study the Coulomb force and the gravitational force, I'll repeat to you then what I'll say now, which is that the Coulomb force is so strong, so unbelievably strong, that it has long ago paired up every positive in the universe with every negative in the universe. So on bulk, the universe is a neutral place, and we live our daily existence completely ignorantly of the fact that there is this huge, immense force locked inside every atom that we just don't notice is there, because the force is so strong that it's neutralized itself by attracting an electron to every proton and producing neutral matter across the entire universe. But if you can just imbalance the positives and the negatives, it massively dwarfs what gravity is capable of. The only reason that gravity rules the universe is because it isn't able to neutralize itself. Gravity is only attractive. There's no repulsive component to gravity that can nullify the attraction, and therefore when you have enough mass, you notice enough gravity. But that's not the same with the electrostatic force. It goes by unnoticed most of the time. Okay, so we got a small problem from a nuclear physics point of view. We know that nuclei are stable, and yet we don't have a clue how the nucleus can remain stable, because we've got this massively repulsive force in the nucleus that's trying to explode the protons away all of the time. And how can it be that the protons manage to coexist with each other inside the nucleus? Okay, so we mentioned this at GCSE. We mentioned that the protons were repelling each other, but we then just whimsically threw in the notion that the neutrons behave like glue and that the neutrons glue the nucleus together. Now, that's fine at GCSE, but it really is not fine at A level. We need to pay proper attention to what can possibly be holding these protons together. And yes, it does involve the neutrons, but it's way more complicated than that. So we need to posit the existence of a new force, one that we've never heard of before, one that we've never noticed before. The entirety of everyday life, as we've just seen, is controlled by the gravitational force and the electrostatic Coulomb force. But now we need to deduce that there exists a third force. And this third force must be very, very, very strong, because it is able to overcome that huge repulsion of the Coulomb force. And yet it must also be a very, very, very short range force that's actually not experienced outside of the nucleus, because if it was experienced outside of the nucleus, we would have noticed it long ago. So we need a name for this very, very strong force that only seems to exist within the nucleus. So physicists, not always renowned for their imagination, came up with the title strong nuclear force, which at least says what it is, and you don't have to worry about it. It was just a placeholder, though. So strong nuclear force was put forward about 100 years ago. About 50 years ago, we got a proper good handle on what it is. And so there is a proper mathematical theory that stands behind that phrase now. And when the mathematical model of what the strong nuclear force was put forward, the mathematical model does have a slightly cooler name. It's called quantum chromodynamics, QCD, which is definitely a postgraduate study if you're interested in that beyond your degree. However, we're just going to stick at A level with this phrase strong nuclear force, and we're going to ask what do we know about it? What can we deduce about it? So here are some things about the strong nuclear force that you can get your head around without having to do the postgraduate level mathematics of quantum chromodynamics. So you should be aware of the fact, you don't need to know why, but you should be aware of the fact that the strong nuclear force is now known to be a nearest neighbor force. That means that its range is actually so very, very short that its range is actually only 1 or 2 nucleon diameters. So nearest neighbors are affected by each other's strong nuclear force. But once you get to 2 or 3 layers of nucleons away from another nucleon, you can't really experience the strong nuclear force anymore. So it's a very, very short range nearest neighbor force. It only extends for 1 or 2 nucleon diameters. It also exists between protons and neutrons. It's a nucleon to nucleon force. The only real difference between the proton and the neutron really is the electric charge, and this is not an electric force. So as far as the strong nuclear force is concerned, it can't really tell the difference between a proton and a neutron. So protons attract protons, and neutrons attract neutrons, and protons attract neutrons using the strong nuclear force. But it's not just attractive. This force is so utterly attractive that if it was only attractive, the nucleons would be pulled closer and closer and closer and closer and closer together forever, and they would end up being compressed to a point. All of the nucleons all in the same place, all at the same time, all compressed to zero volume. So we must also put forward the notion that, yes, it's attractive in the medium distance, but once you get to very, 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 very short distances, kind of within the nucleon radius, it must become a repulsive force so that it starts pushing nucleons apart if they try to get too close. So attractive if they're too far apart, and repulsive if they're very close together. This is not like any other force. This is not like gravity, which just pulls and pulls and pulls. And it's not like the electrostatic force that either just pulls and pulls and pulls or pushes and pushes and pushes. The strong nuclear force is able to do both things at the same time to the same particles. It can attract and it can repel depending on distance. It's not really surprising that it took a whole platoon of mathematical physicists a good 50 years to work out the details of quantum chromodynamics. And in fact, if you do become a postgraduate physics student and you do try to understand quantum chromodynamics, what you need to understand is that an entire branch of mathematics was invented to do quantum chromodynamics. Such was the difficulty of the equations. And to this day, the equations of quantum chromodynamics have not been solved. There isn't a mathematician on the planet who can do the calculations. The equations are really very, very hard. Okay, so here we go. Let's have a little look at the strong nuclear force as a graph, because we definitely can't handle the maths. Okay, so we're going to draw some graphs now. And these are our axes that we're going to use. So across the x-axis, we've got the distance between two nucleons. So if you imagine that proton number 1 is sitting here at the origin, and then we have, I don't know, proton number 2 over here somewhere, what we want to ask ourselves is, at this distance here, what force would proton number 2 be experiencing due to proton number 1 that's sitting over here at the origin? And we'll draw any graphs above the line up here if the force is a repulsive force pushing the two protons apart. And down here, we'll draw any attractive forces where the two protons are being drawn together. So let's start with the one we know about first of all. Excuse me. So I just showed you that the Coulomb force, this is the repulsive one. This one varies with r squared. So this is all a constant here, and these are constants here. The only variable in this formula is r squared. So when r is very, very big, the force is very small. And when r is very, very small, F is very big. So we can draw that one on first. And this is what your Coulomb force looks like. So it's kind of a y equals 1 over x squared graph. There's an asymptote at 0. The force would technically become infinitely repulsive if two protons could get to 0 distance, but obviously they can't get to 0 distance because the force would be infinitely repulsive and we can't provide an infinite force to push them together. So again, another asymptote on the x-axis. If we headed off towards infinity, then at infinity, when the two protons were infinitely far apart, there would be 0 force between them. So this is our Coulomb force. Very, very small at large distances, very, very big at close distances. And between two protons, it's always a repulsive force. If this was a graph of the force between two neutrons, or a proton and a neutron, this red line wouldn't be here. This is just there if there's two protons, which is what we're talking about at the moment. Okay, so here is the graph for the strong nuclear force then. Much, much different shape. So again, at very long distances, it is a very small force, but notice that this one has become 0 much closer than infinity. It's only 5 or 6 diameters of a nucleon before this actually becomes 0, which is why this line is practically on the 0 axis at this distance here. It's an attractive force. So two protons that are near to each other will be attracted towards each other. So will two neutrons, proton and a neutron. But then, as I said before, there needs to be a distance at which the force switches character. So it attracts and it attracts and it attracts, and then there's a peak of attraction. where there is a certain distance between the two nucleons, in which the attractive force would be very, very strong indeed, maximally strong. And then if the two neutrons get closer than that, they still attract, but not as much now. And then there will be a point here at which the strong nuclear force is neither attracting nor repelling. The strong nuclear force actually has a value of 0 at this distance here. And then as we continue above the force axis, the 0 axis, the force suddenly switches character. And if you try to push two neutrons too close together, closer than this point here, then the force becomes repulsive. Gently at first, but then very, very steep. And you can see that, again, this force is tending towards infinity. And if you tried to push two neutrons towards each other to 0 distance, you would require an infinite force to do it. Okay, so you're not expected to be able to understand mathematically where that comes from, but you are expected to be able to describe that it does hit 0 at about 5 nucleon diameters. It is attractive within that, but then it tends towards 0, and there is a point at which it becomes 0 force, and then attraction switches to repulsion. And beyond that, it's a very, very steep graph. You only need to move a tiny amount closer for the repulsive force to get very, very large indeed. Okay, so we need to put these two graphs together now. So there's the Coulomb force again. And we're basically going to add the two forces together. So this is a repulsive force, and this is an attractive force. So you can see that out here, at faraway distances, beyond about 5 nuclear distances, we have that there is a small attraction, but there is a large repulsion. And so in this part of the graph, the Coulomb force is always bigger than the strong nuclear force. And so the repulsion is always bigger than the attraction. And so there is a net repulsion. So if you were a proton over here and another proton over here, and you tried to move this proton a little bit nearer, all through this distance here, the second proton would be feeling a repulsion due to the first proton. So you'd have to push, 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 push to get to this point here. And then the character changes. So the strong nuclear force has been growing all the time. So is the Coulomb force. But the strong nuclear force has been growing with a greater gradient. It's been growing more rapidly. And so by about this point, the nuclear force, the strong nuclear force, has caught up with the Coulomb force and then starts to outstrip it. So during this part of the curve, the blue line is always further from the axis than the red line is. And therefore, during this part of the distance axis, there is net attraction. So if you were pushing your proton in, you'd have to push it a little bit, push, 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 till this point, and then all of a sudden the proton would be snatched out of your grasp, and it would take itself in towards the nucleon after that. So during this point here, the forces will take care of themselves. So when we've been talking at GCSE of fusion, for instance, it's been the force required to get the nucleon to this point, and then at this point, the nucleons will snap together and a larger nucleus will form and fusion will take place. So that's kind of the barrier point that we were talking about at GCSE. And we will come back to fusion later on in this topic. Okay, but we're not finished, because at this point here, the blue line is as far under the axis as the red line is above the axis. And so at this point here, we actually hit 0. So it's neither being attracted nor repelled again, just like it was here. And then after this, the blue line starts to reduce down to 0 and then actually contribute to the repulsion as well. And the Coulomb force has always been repulsive. So in this inner part here, from about this distance onwards, we have net repulsion again. So if you did push your proton in and you pushed it as far as here, it would fly straight back out again. If you manage to get it to exactly this point, it might fly back out or it might fly in. but there is zero force at that point. And then this is the sweet spot, really. This is the point we want to get to. This is our stable equilibrium. If the proton tries to get a little bit too close, it'll get pushed back. And if it strays a little bit too far away, it'll get pushed back. So this is what we refer to as a stable equilibrium. It's a point of zero force, but if you step away from that point, the force tries to return it back to the equilibrium position. This point over here is also an equilibrium position, but we're less interested in this one because this is an example of an unstable equilibrium. So again, at the equilibrium position, the force is zero. That's what we mean by equilibrium, that there's no net force at that point. But it's an unstable equilibrium because if you were to just move a fraction to either side of the equilibrium position, the force will carry you away from equilibrium rather than restore you to equilibrium. So in a stable equilibrium, forces act to keep you in the equilibrium position, whereas in an unstable equilibrium position, forces act to move you away from the equilibrium position. We'll be studying more about various equilibriums in various different contexts throughout the whole of year 13 as we do other forces. But for the context of today, you need to understand that for two protons, that equilibrium position is going to take place at 2 nucleon radius. So 1.2 femtos from this proton at the origin takes us to about there, and then another 1.2 femtometers takes us to the other proton center here. Now, we said before that it was an approximate measurement, and that's because if this Coulomb line wasn't there, if we were dealing with 2 neutrons or a proton and a neutron, actually the equilibrium position would be here at 1 proton radius, because this red line wouldn't be here to counteract the blue line here, and the equilibrium position would take place where the blue line was at 0. So this is your fuzzy region here. 2 protons are held a little bit further apart than two neutrons are, or a proton and a neutron. So this kind of fuzzy area here, this is kind of your region in which your nucleons are separated. So it becomes a difficult thing to say with certainty that the distance between 2 centers are exactly 1.2 femtos or exactly 2.4 femtos, because it really depends whether you're talking about 2 protons or a proton and a neutron, or 2 neutrons. But you can see the principle that there will be an equilibrium either here for 2 protons or here for 2 neutrons or a proton and a neutron. And of course, it's even more complicated than this in a real nucleus, because we're only actually dealing with the forces between 2 nucleons. But in an actual nucleus beyond hydrogen or helium, even helium has three particles in its nucleus. Once you get beyond hydrogen, there will be more than 2 protons in the nucleus. And so there will be pushes and pulls from multiple nearest neighbor sources. And so we find that this gets very, very complicated very, very quickly, which is why the equations are so difficult to solve. You'll be happy to know that you don't have to do any kind of calculating for the strong nuclear force, but you do need to be able to describe the nuclear force in words the way that I have just done, in that it's 0 here, and it's attractive here, and it's 0 here, and it's repulsive here. And that there's an equilibrium position here. You need to be able to describe this graph basically in words. And there are some questions that I'm going to leave you with that you can practice doing that. Okay, that's a very, very complicated graph. I don't think I've spent 10 minutes talking about the shape of a graph in a long time. Is there anyone that wants to unmute yourselves and ask me any questions about this graph or anything that I've just said about it? Okay, I'll push on then. This is the last bit that I wanted to teach you today, this graph. So I'm going to talk you through what I want you to do as private study for the rest of the week now. So if I just talk you through it, it's covered by chapters 24.1 and 24.2 of the textbook. You've got the PDFs on Classroom for this. So if I just show you what's on those pages. So this is the 24.1 double page spread. It reminds you here about Rutherfords Experiment, which isn't very much more than what you did at GCSE. So if you need to remind yourself about the Rutherfords Experiment, please read through that. Then there's this little diagram that I alluded to in one of the slides on Monday, which just gives a little bit more detail about how the deflections are actually taking place. And once you have studied the Coulomb force law, you'll be able to understand the repulsive force between this proton here and this alpha particle coming in here, protons, 79 protons, based on the fact that both of these are positive objects with a positive electric charge. So this paragraph here then kind of assumes a little bit that you've already studied the electric force. So this little bit of algebra here, this formula, that comes from the electric fields topic that we won't do until about January next year. So don't worry too much about this little calculation at the bottom of the page. By all means, read it. It's not beyond you, but the origin of where that formula comes from, you're not going to get to for the best part of a year. So don't worry too much about that formula there at the moment. And then you'll have realized by now that one of the biggest differences between GCSE and A-level is that at A-level, we kind of try to support everything we say with data. So here's some numbers from a Rutherford type experiment that if you were moving your detector around the source and the foil, and you were measuring this angle here, these are the kind of counts that you would get from your detector at different angles. And you can do some analysis on these numbers. And so it's not beyond you at all to answer these 3 questions as part of your private study this week. And then there are these summary questions at the end of the page. There are 6 questions, but again, you would probably be best off skipping out question 5 for now, because it does assume that you've done the electric fields topic, which you have not. However, if you wanted to have a go at it, the formula you need to answer question 5 is this formula here. So if you are happy to just blindly plug numbers into a formula, not quite knowing where the formula comes from, you can answer question 5. But otherwise, that's for your future. Then I'd like you to have a look at 24.2. And everything on this page is something that you can understand. So this is kind of the reminder of what an isotope is and some notation. So we were using a capital A for the mass number, the nucleon number on Monday. So that's just a little bit of notation and a reminder what isotopes is. This is the bit I taught you about with the atomic mass unit. And then this is the bit that I spoke to you about the relative radii of different nuclei and the fact that there is this A to the 3rd relationship. Note in all of this that I spent the best part of an hour doing this with you, and they've managed to squish it into a couple of lines here. So if you were to just read the textbook, you would miss out on a lot of the detail, and you wouldn't, for instance, know how to derive this formula potentially. So if you do ever miss any lessons, do watch the video recordings that I put on YouTube just to make sure that you catch yourself up rather than just reading it yourself through the textbook. This is the strong nuclear force that we've just been speaking about. So there's the Coulomb repulsion that you just did your calculation for. They've done slightly different numbers to use, which is why the answers come out differently. And then they relate it a little bit to some of the work you did for the de Broglie wavelength. What I'd just like to point out, if you pay too much attention to this purple box, is that you know the de Broglie formula as lambda equals h over p, the momentum. And here what they've done is that they've used the value of p to be the energy divided by the speed of light, which is a little bit naughty of them in an A-level physics textbook. I don't really approve. This is truthful. The electrons are traveling so fast that you actually have to take into account special relativistic effects, again, that Einstein enlightened us about. So this is the relativistic expression for momentum. So for particles that are traveling quite slowly, we use P equals mv, but the mass behaves badly when the v gets very large. And so this formula starts, the mass doesn't remain constant for very large velocities. So for very, very large velocities, which is likely in an experiment of electron scattering, where you've sent the electrons through an electron gun and accelerated them up very fast, you probably are going to have very fast moving electrons, and you probably should use the relativistic formula. However, like I said, I do think it's a little bit naughty that they've just snuck that in unannounced in an A-level physics textbook. And if you wanted to do this and you wanted to use P equals mv, your answers won't be very far off the final answer using the relativistic formula. So you're fine if you want to have a go at this using the normal formula of momentum equals mv. Okay, so you can have a crack at those purple ones if you want to, but that's optional. But you can have a go at all of these summary questions down here. They're all quite accessible to you. And then at the end of the chapter, there are some purpley colored pages with some past exam paper questions on. And some of those exam questions refer to the other subchapters in the chapter, so 24.345. But questions 2, 3, and 7 are questions that you're capable of doing based on what we've spoken about on Monday and today. But I have put some annotations on this PowerPoint in case you get stuck, because the past exam paper questions are quite difficult, and ordinarily I would be there with you in class. So when you're having a go at these, by all means, feel free to send me a message or an email if you get stuck, but have a look at this PowerPoint first. So for instance, for part 2A, describe the strong nuclear force, you just need to look at that graph that I was just talking to you about. Working out densities here, you just need to remember what the volume of a sphere is and treat the nucleus as a sphere. Part 2 of this question asks you about a log-log graph. Now, if you don't do A-level maths, you might struggle a little bit with that on what the logarithm is, and you might need to contact me and ask me to send you something about logarithms. If we were in class, I would be able to sit with you and teach you a little bit about logarithms. I don't think there are many of you not doing A-level maths though, so for the majority of you, you just need to note that LG, that's an L, not a 1, LG is what OCR, the exam board, use as shorthand for log base 10. And they use a particularly weird font that makes it look like 1 gram. And I kid you not, I have had year 13 students come out of their final exams crying before now because they mistakenly read the question as 1 gram instead of log, and lost themselves 15 odd marks, which you would think would be very difficult to do. But in the pressure of an exam situation, who knows what people do. So LG is short for log base 10. And what they're asking you to do here, which I'll show you now because it's hard, but then you'll have forgotten about it by the time you come to do it. So don't peek unless you need to. You need to take logs of both sides of this equation. At the moment, this is an example of something called an exponential equation where the index is making a great difference. But what we can do here is if we take logs of both sides of the equation, then you've got log rules for dealing with this, which you have hopefully learnt about in maths. So for instance, you can split this multiplication up into the addition of 2 logs, and then you can deal with this index here by pulling it out to the front. And now hopefully you can see that this is starting to look like y, which is why they've put log r on the y-axis, equals m, which is why this thing's sloping, x, which is why they put log a on the x-axis, plus c, which is why there's an intercept here. So that's your answer for 1 and 2 there. Try not to peek at this when you're doing it for yourself. Question 3 is entirely from the notes from Mondays and Wednesdays lessons. So if you work through either the 2 sub-chapters in the textbook or with this PowerPoint, all of that is straight out of these notes. 7 part 1 is dealing with the electrostatic force, which, one more time, you haven't studied yet, but it is only the red graph that was on slide 23 a moment ago. So it's not beyond you to have a go at that if you wanted to. This one, again, not studied it, but it's the formula for the electrostatic force that was on slide 20. So you can have a go if you want to, but skip out 7a if you don't want to do it. And then finally, when you get down to B part 2, you really, really don't know how to do that yet, and you won't do it until January. So definitely skip out B part 2. If you can finish this week before our lesson on Monday, having read through 24.1 and 24.2 and the entirety of this PowerPoint, make yourself notes if you want to on 24.1 and 2 and this PowerPoint. And then if you can have done the questions from 24.1 and 24.2 and these 3 questions from the end of chapter past paper questions, questions 2, 3, and 7, if you can do all of that by our lesson on Monday, I think you'll have done about 4 or 5 hours work on your physics for me this week. Is that right? Yeah, 4 or 5 hours work for me. And I think you'll be doing really well if you can get that done. So have a go. Drop me an email if you get stuck on anything or if you want me to clarify anything. Otherwise, do you have any questions now about anything that I've said today? Okay, well, I think we're done then. So we're about 15 minutes early, but I'm sure you won't mind that. And unless you contact me, I will see you again at 9:10 Monday morning. Thank you very much.
Cheers, sir.
Thanks, sir.
See you.
Thanks, sir.